Assalamualaikum and hi guys. I hope you guys are doing fine at home. So today I will go through lecture 6 slides. So if you see on the slide, it shows the topic that we are going to discuss today is flow rates and mass conservation equation. So these are the contents of this lecture. It looks quite short, but I will divide it into two parts. In the first part, I will just talk about flow rates, and in the second part, I will derive the Reynolds transport equation and mass conservation equation. Okay? So fluid motions are governed by three conservation laws. So what are the laws? The mass conservation law, the momentum conservation law, and the energy conservation law. So the basic concepts for analyzing fluid motion have been described in last lecture. Are you sure? Last lecture? Last lecture or the lecture before that? Lecture 4. It's in lecture 4. So I hope you guys have watched lecture 4 video so that you know what I'm talking about lah. Okay. So after this, in part 2, I will discuss on the general control volume analysis and the application to conservation of mass or mass conservation law. Okay. So to describe the fluid flow, normally we use velocity, right? Okay. So instead of velocity, we can also use flow rate. Okay. So flow rate, when we talk about rate means the parameter you divide by time. Okay. So most of the time we use volume. So volume flow rate. Volume flow rate means volume we divide by time. Okay. That's why you get meter cube per second. Okay. So by definition, volume flow rate is the volume of the fluid that is passing through a given cross-sectional area per unit time. Okay. So if you see here, volume, okay, volume divided by time. So you get U delta T delta A divided by delta T. Basically you get U delta A. So I will write this. Okay, so volume flow rate is basically volume you divide by time. So volume, let me change. So volume is area times distance. So let's say L is the distance. You divide by time. So L divided by time, distance you divide by time, basically you get velocity. Okay. So this velocity, this is the average velocity. So other than V dot, we can also use this notation Q for volume flow rate. So in the simpler form, this will become Q equals to AV. Okay. So Q equals to AV. It's in meter cube per second. Alright. So for ideal fluid, if you still remember in lecture 4, we have ideal and real fluid. Okay. So for ideal fluid, the velocity is uniform, meaning velocity is the same. Okay, throughout through the cross-sectional area. So when you find the average, it will be the same lah. However, for real fluid, you have a velocity profile. The velocity is 0 at the wall, okay, due to the no slip condition, and velocity increases as you go far from the fixed wall, and it becomes maximum at the center. But this nice parabolic shape can only be seen in laminar flow. For turbulent flow, the shape will be different. Okay. So which velocity you want to take here? So to get the exact velocity, you must integrate this with respect to the area. Alright, so you must get the velocity profile equation to solve this lah. Okay. So other than volume flow rate, okay, you can also describe the fluid flow in mass flow rate. So mass flow rate is mass you divide by time. So mass divided by time you get in kilogram per second. So mass divided by time, mass is density times volume. So volume divided by time is basically volume flow rate. So you will get rho u dA. Okay, I will write this again below this. So m dot is dm dt. So m is rho times volume dt. So this is volume flow rate. So from here, the volume flow rate is rho v dA. So in a much simpler form is m dot rho a v or rho q lah. Okay, it's in kilogram per second. Okay, but for real fluid, you must integrate it with respect to the area. Okay, rho v dA. Alright. So you can also describe the rate, the flow rate for any extensive property. Okay. So what is the extensive property? It's the property that varies directly proportional to the mass. So meaning that if mass is changed, this extensive property will change. The example is momentum, kinetic energy, enthalpy. So momentum you should have momentum in x, y and z lah. Okay. So let x be the notation for this extensive property. It can be kinetic energy, it can be momentum, enthalpy and many more lah. Okay. So I will do the derivation on how to get this flow rate for the extensive property. So you want to get this, right? So what is the equation? Okay. So let x, small x, be the specific form. So specific form means you divide by mass. Okay. Alright. So any change in the dx will cause a change x. This is from here lah. From here. Okay. So if you write in rate dot, this will become rate. Okay. So this will become x. This one I get from here. X rho v dA. Okay. So to get x, I integrate x rho v dA. Okay. So this is for ideal. Ideal, and this is for real fluid. You have to integrate. Okay. So for the V, you must take the average, right? But most of the time, the velocity profile is given in the equation for the velocity profile will be given. So you just replace into the equation. Into this. Okay. So this is the example. Before that, other than flow rate, you can also find the mean value. So the mean value of any extensive property is the uniform value of the extensive property which would give the same flow rate as the real flow. Okay. So how do you get the mean value or the average value? You put a bar at the top here. the flow rate of the extensive property divided by mass flow rate. So you get the average, or the mean value. Okay. Alright. The most commonly used shape, to I mean the common shape, the common shape for a pipe is cylinder, cylinder. So the elemental area or the differential area for a cylinder is 2 pi r dr. So remember that we have the dA here, dA. You can replace this with 2 pi r dr, okay? And 2 pi is constant, you put outside, okay? R dr. So normally it is to get the value, you have to integrate from 0 to maximum radius. Okay? Similar this, you put the 2 pi outside. This row can also be put outside because it's a constant. V R dr from 0 to maximum radius. Similar to this, 2 pi x can also be put outside, so a constant. V R dr from 0 to maximum radius. Okay? Alright, save this first. Okay. So these are the example of extensive property flow rate. You have kinetic energy, momentum, enthalpy. Okay, let's do this example. This is the velocity profile. So as I mentioned, the velocity profile is normally given for a real fluid in a pipe flow. Okay, where U naught is the maximum velocity. R is the radius of the pipe. So you need to determine the mass flow rate, the x momentum flow rate, and the mean value for the x momentum. Okay, so let's do this. So we have U naught 1 minus R over R capital square. Okay, you rearrange. In this question, it uses U as the velocity. In the derivation just now, I used V, right? So you can use U or V for velocity. So U naught, you rearrange this, okay? Okay. So this look like a nice parabolic shape velocity profile. So how do I know? How do I know? How can you know? Okay. Let's say this is U naught. This is the center with the radius R. Okay. Okay. Here U should be 0. So if you replace the equation R with 0, okay, R0 which is at the center, so U equals to U naught, okay, 1 minus 0, so 1 lah. So basically at the center, U equals to U naught which is maximum lah. Okay, if you replace R with capital R, so you should get U. Okay, you should U naught 1 minus R capital divided by R capital, you get 1. So basically you get 0. So this should be 0 lah. Okay, so at the fixed wall or at the wall of the part, you should get U equals to 0 due to the no slip condition. Alright. Okay, so the question asks you to find m dot, the momentum in x direction dot, and the momentum mean value. Okay. Okay, m dot, how do I get? I just use the equation that we have just discussed just now. which is 2 pi rho. Okay, this u, I leave it as u, r dr, r dr. Okay. So this u, I replace with the equation here. So rho, okay, u naught I put outside. So this should be 1 minus r over r square r dr. So I times with r, I should get 2 pi rho u naught. Normally all the constants are put outside. So r power of 3, r capital power of 2. Be careful on this. You have to, by right, you should know how to do the integration. 2 pi rho u naught r square divided by 2 r power of 3 divided by 3 r power of r power of 4, you divide by 4. You divide by 4 power r power of 2, from 0 to maximum radius. So 2 pi rho u naught, replace r power of 2 divided by 2 minus r power of 4 divided by 4r power of 2. This can be cancelled. Okay, make sure you cancel. So this one, 2 pi rho u naught times 2 to get 4. So 2r power of 2 minus r power of 2 divided by 4. So you should get, okay, this can be cancelled. So you should get pi over 2 rho u naught r power of 2. Alright, so this is the answer for the first question. M dot. Let's save this first. Okay. So the second question asks you to find m dot, the rate for the momentum. So before that, I will need to show the momentum in specific form. The momentum in specific form is this. Okay, momentum is mass you divide by mass you times with velocity. Okay. Okay, and m. So this will be cancel lah. So you get u only lah, u in x direction, which is same like in the question lah. The question goes to x direction. So therefore, which is u lah. Okay. So therefore, when you write this, you want to find the flow rate, right? So you use the same equation like what you did previously. Okay, which is u. Okay, this in the example or when I derive it, I use x, right? X, and then I times with okay. I have x, u, and then I have r dr. Okay, so this x is now replaced with this. Okay, so by right, you should get this as u square. Okay, because the last time we used x as a notation for the extensive property. So now we have this extensive property, which is the momentum in x direction. So we get this specific form as u. Okay, so therefore you get u square. So you replace with the equation just now, the u equals to u naught times 1 minus r over r square. Okay, so you should get this as u naught square, and then we have 1 minus r over r square, and then u square. You have to square both lah. Okay, and then r dr. Okay, so you put the u naught outside because it's a constant. How do you integrate this? Okay, you must simplify it first. Let r over r square equals to y. Okay, so 1 minus r over r square uh, square is equal to 1 minus y square. Okay, so what do you get here? Sorry, it's not square. Yes. So 1 minus 2y plus y square. So you replace 1 minus 2 r over r square plus r over r square and then square. Okay, you square here, you get 4 lah. Okay, so this you put inside this equation. You should get 1 minus 2 r over r square plus r over r power of 4. Then you still have another r here. So r, dr. So 2 pi rho u naught square. Sorry, this should be r, right? Okay, 0 r. Okay, times with r, 2r power of 3, r power of 2, plus r power of 5, r power of 4. Then everything is integrate with respect to the r. So 2 pi rho u naught square. R square over 2, 2r power of 4 divided by 4r power of 2 plus r power of 6, 6r power of 4. Okay, then you replace with capital R, 2 pi rho u naught square, r power of 2 divided by 2. So this one becomes r power of 4 divided by 2r power of 2. This one cancel, become 2. This look the same, right? So it can be cancelled. So plus r power of 6. You divide by 6r power of 4. Cancel. This becomes 2. Okay. And then this 6 with 2 becomes 1 over 3 rho u naught square r power of 2. Okay, so this is the answer. Alright. Okay. And the last question asks you to find, save this first. Save as, just now it's a velocity profile. 2, right? So 3 lah. Okay. Okay. The last question asks you to find the mean value. The mean value for the momentum rate in x direction. It's equal to momentum rate divided by mass flow rate. Okay, so momentum rate is pi over 3 rho u naught square r power of 2, and mass flow rate is pi over 2 rho u naught r power of 2. Cancel, 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 cancel. So what do you get? 2 over 3 u naught. Okay, so if you have the maximum velocity, then you can get the value. Alright. Okay. So this is how you answer lah if you want to solve for the real fluid atau velocity profile, especially for laminar. Okay, this is quite similar, but just that it is for a square duct, and I won't do this. You can try this on your own. What's the difference is that the DA is different. Okay. Alright, so for this topic, I will talk in another part, which is part 2. So, see you guys again. Thank you.